Keystones Unearthed. I'm August Vane. Tonight. The rocks that walk across the desert by themselves. Death Valley holds the record for the hottest air temperature ever reliably recorded on Earth, 56.7 degrees Celsius, measured at Furnace Creek in July of 1913. It is also one of the driest places on the continent, receiving under 6 centimeters of rain most years. It's a landscape shaped by extremes, a basin sitting 86 meters below sea level, ringed by mountains that trap heat and starve the valley floor of rainfall. And tucked into its northern reaches is a smaller, stranger basin called Racetrack Playa. Racetrack Playa is a dry lake bed roughly 4.5 kilometers long, so flat that its elevation varies by only a few centimeters across its entire surface. In the right light, it looks almost artificial, like a poured concrete floor. What makes it famous isn't the flatness. It's the rocks. Scattered across the playa are hundreds of stones, ranging from pebbles to boulders over 300 kilograms, each one trailing a long groove carved into the dried mud behind it. Some trails run arrow straight for hundreds of meters. Others curve gently, or make sudden 90-degree turns, or double back on themselves entirely. Two stones sitting a meter apart can have trails that go in completely different directions. Nobody, in more than a century of recorded observation, has ever directly witnessed one of these stones move. Not a park ranger, not a geologist camped nearby, not a tourist with a camera. The stones only ever seem to move when nobody is watching. The earliest written references to the moving stones appear in prospector and surveyor accounts from the early 1900s. At the time, the most common explanation offered was the simplest one: someone was moving them as a joke. That explanation collapses quickly once you consider the setting. Racetrack Playa sits at the end of a rough, unpaved road, hours from the nearest town, in a place where daytime temperatures regularly exceed 45 degrees Celsius. It is not an easy place to sneak out to at night with a truck full of boulders. By the 1940s, scientists had taken the mystery seriously enough to start proposing physical mechanisms. In 1948, geologists Jim McAllister and Alan Agnew mapped the trails formally and suggested that powerful winds, funneled and accelerated by the surrounding mountains, might be strong enough to push the stones across mud softened by rare rainfall. The wind theory had real problems. Wind tunnel calculations suggested that moving the heaviest stones would require sustained winds far beyond anything ever recorded at the playa. And wind alone struggles to explain trails that turn sharply, since a steady gust should push a rock in a fairly consistent direction. Other theories piled up through the mid-20th century. Some proposed a slick film of algae coating the mud after rain, reducing friction enough for wind to do the rest. Others speculated about magnetic fields, or even, at the fringes, something stranger than physics. In the 1970s, Caltech geologist Robert Sharp and his colleague Dwight Carey took a more rigorous approach. They selected 30 stones, gave each one a name, staked out their positions precisely, and returned to measure them repeatedly over 7 years. Sharp and Carey's long-term study conclusively ruled out human interference. The movement patterns were far too irregular and the site too remote for any hoax to explain consistently. But their data didn't cleanly support the wind theory either. Some stones moved repeatedly. Others, sitting in identical conditions, never moved at all. The mystery sat there, unresolved, for another 3 decades, a genuine open question in geology, discussed in textbooks and documentaries, always with the same honest caveat that nobody had actually caught the mechanism in action. In 2011, a new team took a different approach entirely. Geologist Richard Norris and his cousin, engineer Jim Norris, secured a research permit and decided to instrument the playa directly rather than theorize from a distance. They fitted 15 stones with custom-built, motion-activated GPS units, precise enough to log movement down to the centimeter. They installed a weather station to continuously record temperature, wind speed, and precipitation. Then they set up time-lapse cameras with a wide view across the entire playa. Given how rarely the stones seemed to move, the Norris team expected the project could take 5 to 10 years before a real event happened during an active camera cycle. They were prepared for a long wait. They didn't have to wait nearly that long. In December of 2013, an unusual overnight rain left a shallow pool of water across part of the playa, only a few centimeters deep. That same night, temperatures dropped well below freezing. A thin sheet of ice formed across the surface of that shallow water overnight, only a few millimeters thick, fragile, but just rigid enough to hold together as large floating panels once the sun came up and the ice began to break apart. At sunrise, as that ice sheet fractured, gentle morning winds, nothing close to the hurricane-force gusts earlier theories required, caught the floating ice panels and pushed them slowly across the still liquid water underneath. Each floating ice panel, with a stone frozen into its underside, acted like a tiny icebreaker ship, gliding across the wet mud and shoving its embedded stone forward, carving a fresh trail as it went. The team's cameras captured more than 60 stones moving that single morning. One stone track that winter traveled over 200 meters in a single event. The trail it left matched, in every visible detail, the exact type of trail geologists had been finding and puzzling over for more than 100 years. The mechanism turned out to require an unusually specific, narrow combination of conditions: a shallow flood, a hard overnight freeze, ice thin enough to break into movable panels, and a gentle morning wind, all arriving within the same short window. That rarity explains everything that had confused researchers for decades: why some stones moved and others didn't, why movement seemed to skip years or even decades, and why nobody had ever managed to witness it directly despite generations of curious visitors. It's one of the few entries in this kind of story that ends with a fully confirmed, tested, repeatable answer rather than a lingering theory. What solved it wasn't a single insight, but patient, well-designed instruments left in place long enough to catch a process too slow and too rare for anyone to witness by accident. Death Valley itself sits within the Basin and Range Province, a vast region of tectonic stretching that has been slowly pulling the Earth's crust apart for millions of years, creating exactly the kind of enclosed, sediment-filled valleys that produce flat, dry lake beds like Racetrack Playa. The 2011 to 2014 GPS study wasn't the first serious attempt to photograph the phenomenon in progress. In the 1950s, geologist George M. Stanley spent years photographing and mapping the trails, and was among the first to seriously propose that ice, not wind alone, might be involved. The final mechanism, once confirmed, was published in the journal PLOS One in 2014. Researchers termed it ice shove, a process where thin, wind-driven ice sheets exert just enough lateral force on embedded rocks to move them across saturated, nearly frictionless mud. What makes ice shove so hard to catch is the narrow window it requires. The playa needs rain rare enough to leave only a shallow pool, a freeze cold enough to form ice but not thick enough to lock everything solid, and wind gentle enough to glide rather than shatter the ice sheet. The playa's popularity created its own modern problem. In 2016, visitors illegally drove vehicles onto the wet surface, leaving deep tire ruts that will likely remain visible for decades, since the extreme dryness means the mud rarely gets wet enough to naturally smooth itself out again. The National Park Service responded by increasing signage, ranger patrols, and public education specifically asking visitors to observe the trails from the playa's edge rather than walking or driving across the fragile surface itself. Scientists studying the sliding stones have noted the mechanism may have relevance well beyond Death Valley. Similar wind and ice interactions have been proposed, though not confirmed, as a possible contributor to surface features observed on other planetary bodies with thin atmospheres and ice cycles. Racetrack Playa isn't entirely unique on Earth either. Similar dry lake beds, called playas, exist across the American Southwest and in parts of Australia, though none have produced documented moving stone trails on anything close to the same scale. What made Racetrack Playa the right natural laboratory for this phenomenon was a rare combination of factors: a source of loose rocks eroding from the surrounding dolomite cliffs, an unusually flat and smooth mud surface, and just enough occasional rainfall to periodically flood it shallowly. The stones are still out there today, resting at the ends of trails both old and fresh, in a national park that now actively protects the playa surface, asking visitors to stay off it entirely so the fragile mud crust isn't disturbed by footprints. Somewhere out on that flat, cracked ground, the next rare morning is already being counted down to another shallow flood, another hard freeze, another quiet slide across the mud that nobody will be there in person to see happen. Look at the evidence. Decide for yourself. I'm August Vane.